All right, ladies and gentlemen, I wanted to welcome you to today's webinar. My name is Christopher Urbane. I'm calling in from lovely Blacksburg, Virginia. Today's educational program is going to be inspecting your data, how to identify potential data integrity problems using simple graphs. Our presenter is Martin Carignan. He's a consultant at Different, and he's joining us from up in Canada towards Montreal. We are recording today's program for educational purposes, and it will be uploaded to our YouTube channel for the ASQ Inspection Division. I just want to remind everyone that this information being presented tonight is just for educational purposes only. It is the viewpoints of the presenter and not necessarily the viewpoints of the ASQ organization. We will be posting a video link of today's presentation within 24 hours of the presentation and the webinar. So for those of you that have not dialed in, you can also call in to a phone number that is listed in case you have any issues with the audio for the program. We're looking forward to your comments and questions. If you have any questions, you can type them into the chat box, and what we'll do is we'll do our best to go through the questions that have been typed in during the presentation once Martin wraps up his presentation. So once again, please make a warm welcome for Martin. And Martin, the show is all yours if you're ready to take over.
Thank you, Christopher. So as Christopher told you, I'm calling you from Montreal. So I am under a snowbank here. We received a lot of snow. So hopefully this will be a hot topic enough to warm us up. So the title is Inspecting Your Data, and so how we can identify some issues with our data using a simple graphs. The presentation, so the goal is only with the simple graphical tools, give you some tips on how to identify if there could be some data integrity issues. So we'll cover three topics. I'll be talking about how combining an histogram with a normal quantile plot, how this can help in identifying cheating, and what's the difference between sorting and cheating. And we will end with the last topic being the Benford's law, which I will present the law and how it can help identifying if people are just coming up with numbers, inventing numbers, and not entering real numbers. So first, the histogram and the normal quantile plot. So before we learn how we can see cheating in the histogram, I'll just quickly explain what an histogram is. So on the right, you have yield data, which is a percentage. The higher, the better. And it's a yield value per month. And on the left side at the bottom, what you have is the histogram of those values. So on the x-axis, you can see those are the yield values, and they are separated by intervals that have a range of 5. So for example, from 68 to 73, and then 73 to 78. The height of the column corresponds to the frequency, which is the number of observations we found in that interval. So for example, if we look at the interval between 73 and 78, here it's at a height of 6, which means we have 6 observations in our data set that are within that interval. And those observations are identified in red on the right. So if you look at what's in between 83 and 88, you should find 2 values there because the height of the column is at 2. Often a distribution which is often used in practice, and it's also a distribution which approximates a lot of natural phenomenon, is the normal distribution. So on the histogram that you see at the bottom right, you can see that this distribution looks like it's bell-shaped. So it's symmetrical, and it has a single peak, a single mode. And just above that graph, you see a normal quantile plot, and I'll explain that plot a little bit later. But on that plot, you know the data is normal when the points, which are the observations in your data set, are distributed randomly around the red line. So the normal quantile plot, how it works, for example, if we assume the data on the right is the yield data. So if we assume that the yield data has a normal distribution, we take the average yield, which is 79.2, and the standard deviation of the yield, which is 5.3. And if we assume that the data coming from this data set has a normal distribution, then we know that the median is equal to the mean. So you see on the right, the median, which is at 0.5, which is a little bit which is a little bit hidden here, the 0.5 corresponds to the value of the mean on the x-axis. And we can also see that if the distribution is normal again, with a mean of 79.2 and a standard deviation of 5.3, the 90th percentile should be at 83.7. So this is how this red line is built. It's assuming we have a normal distribution. What would be the different percentiles? And what you can see is that the data points are following that line, mostly being randomly distributed around the line, which means we have no indication that this data set is far from being normal. So first, let's look at one thing that could happen in practice is if you take your data, you plot it on an histogram and a normal quantile plot, because often having both on the same page allows us to make sure that we don't miss any signal. So if we look at the histogram here, this histogram could look a little strange because typically what you expect is to see some columns that would continue on the right, falling down, and also continue to fall down on the left. In addition, the normal quantile plot at the top has also a strange look. Instead of being a straight line, so randomly distributed around the red line, it is S-shaped, which is an indication of potentially something a little bizarre here. So when we see that, we could be questioning what is really happening here. Is it normal? What could cause this? On the next page, what we see, we just added the specification limits on what we measured. So we know those measurements should be between 45 and 75. Which are represented by the two blue lines. And what we can see here is that the distribution stops at the spec limits. Normally, we would expect the distribution, the histogram, to have columns that would continue, but they suddenly stop at the spec. So this is an indication that there could be some sorting of the data. So it could be sorting of the products. For example, the situation could be you receive product from your supplier, and your supplier has those blue specs. And because your supplier knows he's producing products that are outside of specs, he's performing 100% inspection. On your side, you do some inspection of the incoming products. You don't necessarily inspect everything. However, when you look at the data you see from your inspections, you get this histogram. So this could be an indication that on their side, they're testing everything and they are rejecting everything outside of spec before they send you the product which is inside specs. Or it could be an indication that, for example, your data set only contains data from good products. For some reason, the products that were outside of spec are not included in your data set. However, the thing is, it could be interesting to ask questions to better understand what is happening. On the next graph, what we see on the histogram is a little different, and it's the difference between what I call sorting and cheating. So what we see here, again, typically what we would expect to see the columns falling gradually on each side. And what we see here is a little different because the columns that are within spec, but right next to the spec, are higher than what we would normally expect. And the column that we would expect to be just outside of spec, actually there's no column there, it's an empty hole. When we see something like that, typically why do we see this? It's because probably people obtain, or the process gave some results that were outside of spec, but barely outside of spec. And what people did, one thing they could be doing is, gee, I obtained a 104.2. It's just outside of spec. I will enter 104, which brings the observation at the spec, so within spec. Or I obtain a 96.1. I'll round that to 97, which brings the data back just inside of spec. So that's why those two columns typically just within specs are higher than expected. And outside of spec, because they're not that far, people bring the data, bring the observation back in. So of course it could be data that they just come up with. So instead of entering 96.1, somebody enters 97. However, another practice I've seen is not, it's like cheating, but with a good consciousness, which is I obtained 104.3, and I know there is measurement error. So I'll test again. And the second test, I obtained 103.9. Oh, so this is probably the good result. So what I enter is 103.9, which is within spec. And same thing on the other side. I test, I obtain 96.4. And I thought this is probably measurement error. Test again, obtain 97, and that's what I put as the test result. So of course, if you look at this practice with statistical eyes, it's really a strange practice. Why the second result would be better than the first result? Both results have measurement error. So this is a practice that can be questioned. And this type of histogram, I've seen it quite often, especially when we look at data, test results that are manually entered, and on parameters that were never looked at using an histogram, so people never noticed before. Now let's look at this data. It's my last example using an histogram and a normal quantile plot. Those data, you can see on the left graph, it's a trend chart. So it's observations over 13 days. We have one observation per day. On the y-axis, we see it's a characteristic called BOD5. BOD5 is a biological oxygen demand. It takes 5 days to get the results, and it's something we measure in water that we send back to the river. Ideally, this value is as low as possible. And this is the process. We look at the process data, and we see the graph on the left, which is no real obvious trend. Everything seems normal. On the right, you have an histogram, and there, of course, it looks a little strange, but, you know, it's only 13 data points. all histograms look strange with 13 data points, so we're not that concerned. But here there is one graph missing. It's the normal quantile plot. And I really recommend doing that graph because it allows to see things you typically could miss with those basic graphs, a trend chart and an histogram. So here we added the BOD5 data on a normal probability plot. And what we can see here is on the x-axis, it's the BOD results. And what is strange, the points are kind of randomly distributed around the blue line, except for the last point. There is a row of 4 points there, exactly at 360. So we're wondering why. Going a little bit deeper, we learned that there is an upper spec limit. So the BOD5 should never be above 360, because if you're above that, you could be in trouble. So we added the spec to the graphs, and what we notice now is a strange phenomenon. It's the process stops at 360. We see the 4 data points on the normal quantile plot at the right being exactly at 360. So here it's probably also a case of cheating. So people probably obtain results above 360 and just entered the number 360 so they wouldn't be in trouble. And it was a test that was manually entered. So this is the first part showed you with an histogram and a normal quantile plot how to detect potential sorting or potential cheating. The last graph I want to show you is a graph associated to a very interesting law, which is called the Benford's law. It's also known as the first digit law, which states that in any listing, tables of numbers, or actually in many situations, we can see, if we study it, that the digit 1 tends to occur with a frequency of 30%, which is much greater than what we would expect if we were just doing a simple calculation, which is, okay, the first digit, what can it be? It's a number between 1 to 9. So 1 could happen theoretically 1 time out of 9, which is 11% of the time. However, when we study many data tables, I don't know, the salary of people or the many types of data set, we can see something strange. The digit 1 appears often around 30% of the time in the first digit. So the Benford's law is actually a law with a formula. So, and the formula is the following, if you want eventually to implement that in Excel. So the probability of any number D from 1 to 9, the probability of that number being the first digit of any number is equal to the formula you see below. So this is what gives us our 30% for number 1 being in the first digit. If we apply the principle to the first digit in a number, and then we look at what's the probability of having number 1, 2, 3, 4, 5 up to 9 in at the second digit, third digit, and fourth digit. What we see is that the digit 1 to be in the first place, so the first number of a number is the first digit of a number is 30%. 2 is 17, 3, 12, and it goes down like that. However, number 1 If we look at the second place in a number, then the probability falls very rapidly to 11%. And it's number 2, which is higher. And if you look at the fourth place in any number, then any number is almost equal. And this strange thing was first noticed by a guy named Newcomb because he was looking at logarithm books, and he saw that the first pages in the logarithm book, and those pages were often containing, having numbers starting with a 1, were much more worn than the later pages. So he said, how come? Why? And this phenomenon also was rediscovered later by a guy named Frank Benford, and he's the person who got credited for the discovery, so that's why we call it the Benford law. What's the logic behind the law? The logic is the following. So if we have a data entry that begins with the digit 1, that in terms of proportion, it has to double in size before it begins with digit 2. So for example, if I have a value of 10, then for that number to begin with digit number 2, 20, I have to add 10 to it, so it's like a 100% increase there. However, if the first digit of a number is 9, then it only has to increase proportionally by 11%, so that the next digit to become a 1. So for example, if my number is 90, for that number to become 100, I just need to add 10, and 10 over 90, it's only 11%. So in terms of proportion, that's why we have more numbers starting with a 1 than we have starting with a 9, typically in many data sets. So, and what also we discovered is that when people are inventing numbers, they are really unlikely to follow the Benford's law. So often manipulated numbers or invented numbers that are chosen by people will not follow the law. And there's a Mark Nigrini, who was a professor in accounting. He used that principle to detect fraud. So if somebody is trying to change some numbers, modify some numbers, falsify some number, often they will invent those new numbers, and typically they tend to use too many times the number 5, 6, or 7 compared to using the number 1, which should appear 30% of the time as a first digit. So typically when you don't respect that law, it doesn't mean that there is necessarily manipulated data, but it could lead to asking more questions. And here I'll give you an example taken from an article which is showing us how it could be applied in practice. So here we have a small business owner who used to be really hands-on in his business because he only had one store, and now the stores are growing, so he cannot be as much hands-on as he would like to be. And so time has passed, and now he's a bit concerned about having bookkeeping errors or potential fraud. So he used Excel to analyze some of the store's data, the disbursement data. So he looked at the data, and he saw that when he was looking at the first digit of any of all the numbers he collected on the disbursement of a store, he could see something strange. So looking at the Excel file here, what we have is on the x-axis, we have the digit 1 to 9. Then on the right, the y-axis, the vertical axis, it's the percentage of the time we're seeing a number starting with that digit. And the blue lines are representing what we would expect according to Benford's law. So you can see there that the digit 1 has a blue line at 30%. And the purple columns are representing the number of times that digit was seen in the data set. And what he noticed is that there's too many 5, 6, and 7. And there's really not enough 1 and 2. Again, for the first digit of all the numbers he looked at. Then he looked at the second digit, which is a different distribution. Again, in the blue, you have what we would expect according to Benford, and in purple, what he saw with his number. And he could see that number 6 and 7, or he was seeing that too many times as a second digit compared to what he would expect from Benford's law. And then he did a test, the last test, what the first 2 digits combined. And there we can see that when we combine the first 2 digits, the 56, which is the very high yellow bar, and the 67 are the 2 numbers that are appearing very often, and much more often, the 2 numbers, the 2 first digits, much more often than again what would be expected according to Benford. So with that, he had enough evidence for him to go deeper and ask questions and look into the books. So he pulled sample of the disbursements that were starting with the digits 56 and 67. And what he discovered is that those were made to an unfamiliar vendor that he did not know. And when he went deeper, he saw that actually that vendor did not exist. The payments were going to a personal account, the accountant account. So that's how he discovered the fraud. So, of course, the Benford law is a law that often applies, but it doesn't always apply. It doesn't apply to all situations. And so there can be many false positives, meaning the law doesn't apply, but you have no fraud still. So it's not because the law doesn't apply that it means you have a fraud, but it could be interesting to go deeper if it's possible. And the opposite is also true. It's not all type of fraud that can be detected using Benford's law. Especially now that you know the law, it's going to be easier to fraud. Just so you know, in terms of support, at Différence, we have an Excel add-in that allows to easily analyze data. And here it's just a screenshot of the one-pager analysis when you analyze only one variable. So you get the box plot at the top right, the histogram here where we see that could be something strange, the normal quantile plot, the control chart. And many other softwares can do that. And the good news is that we have a free Excel file that allows to test the Benford law. And because my background is in statistics, I thought that something was missing there, which is on the proportion of any number digit that we see, there should be a confidence interval because the precision of the proportion depends on the number of numbers you had in your data set, number of observations. So I don't know how we'll organize that with the ASQ division, inspection division, but it would be easy for me to send you that Excel file that allows to apply the Benford law on the first digit, the second digit, and the combination of the first two digits with confidence intervals. So, for example, how I would interpret this one, this output is the blue dotted line is what I would expect as a proportion according to Benford's law. The black dot is the proportion I saw in my data set. So here in this data set, I see that I have approximately 7% of my numbers that starts that has a 1 as a first digit, which is much lower than the 30 expected. And the green line is the confidence interval around that number. And when the confidence interval doesn't cross the blue line, this is an indication really that the proportion in my data set is really not at the Benford expected rate. So, and in this data set, I would see that the digit 1 is much lower and significantly lower than the 30% expected, and digit 8 and 9 are much higher. The other digits, since they cross the blue, the green vertical bar crosses the blue line, I cannot say really that they are different from what would be expected using the Benford's law. So the conclusion, I think if you use an histogram in combination with a normal quantile plot, both together are really useful in identifying strange stuff like potential sorting and cheating. And you saw that in my examples, to identify that, it's even better if we can add the specs on the histogram and the normal quantile plot. And we also saw that the Benford law can also be very helpful in detecting manipulated data, because people are not good when they come up with numbers. They have typically a tendency to use the 5, 6, 7 as a first digit much too often. So that's the end of my presentation. If I'm really open to answering your questions. I see one. What are the assumptions in Benford law? I see that from the chat. One of the assumptions is that for the law to apply is that the numbers are not naturally bounded by something. For example, if I analyze the prices of products in a store, if they often use the strategy to end with $19.99 so that my brain doesn't get it's $20. So often that strategy is used, so $14.99, 9.99. Then of course you will probably see number 9 appearing much more often than the Benford law. Also, other circumstances could be when there is really a physical limit, and you're often at the physical limit. So you, for example, my maximum value I can get is 75, and I'm often at 75, then the law won't apply. So there are multiple situations like that when the numbers cannot really take many values or have often very specific values where the law won't apply. Other questions? So I think we can end the presentation.
Excellent. Thank you very much, Martin. Are there any other questions? I saw another one come in. Have you used a control chart as it preserves a timeline and then applied pattern rules to identify any cheating? If yes, what type of rules are used?
No, for me, from my experience, and on this one I could be wrong, but really from my experience, when I discovered cheating, it was typically with an histogram combined with a normal quantile plot. On the control chart, I typically did not find cheating there. So I don't know, perhaps another participant by the chat could have some type of rules there, but my experience, it's not from control charts, even adding run rules, whatever, that I discovered cheating. I have a question from somebody. Can you hear me, Martin? And the answer is no. I think you are muted. The communication has to be through the chat, I guess.
Yes, that is true. The other question was, how do people get a certification of attendance? Those will get automatically emailed out at the end of the presentation once we disconnect. Once again, I want to thank Martin for joining us for this great presentation. If you would like to contact him directly, his personal contact information is on the screen. And once again, the presentation will be recorded and uploaded to our YouTube channel for ASQ Inspection Division. So you should be able to find this by just Googling or doing a quick search on YouTube, and that presentation should be there towards the end of the week. What I'll do is I'll wait another 30 seconds in case there's any other questions or comments. Yes.
What I would like to add is, if you're interested in getting the Excel file that applies the Benford law, you can just send me an email or contact me through LinkedIn and give me your email address, and it will be my pleasure to send you the Excel file.
Excellent. Thank you all for joining this evening. Thank you again, Martin. If there's any questions or comments that don't get addressed this evening, you can feel free to contact one of us, and we'll do our best to get back to you.
Thank you. Thank you all.
Have a good night.
You too. Bye-bye.